Welcome, everyone. Thank you for joining today's lab tour. My name is Christina. I'm one of the MS advisors in the ACE department. And today we have Yi Kuan, who is one of the current PhD students working in Professor Trong Nguyen's lab. I'm going to start by playing a video that describes a little bit of the lab and the work that's being done. And then if you have any questions after, please feel free to either unmute yourself or send your question in the chat, and we'd be happy to answer it for you.
The Video Processing Lab at UC San Diego currently focuses on the theory and applications of deep learning networks and image video processing techniques on several application areas, including health analysis and monitoring, autonomous driving, and XR virtual reality. In the health analysis/monitoring area, the lab is working on several projects: multimodal retinal image processing platforms, fall risk assessment systems, and ultrasound robotic systems. In the autonomous driving area, the lab is interested in developing algorithms to detect the driver's gaze for monitoring purposes, as well as developing algorithms to detect and track objects based on the novel human-centered camera system. In the XR virtual reality area, the lab proposes an efficient and robust system for digital human models. The lab presents a novel video defencing system providing a clear view of the fence scenes in the video. To provide accurate fence masks for defencing, the lab proposed a fence segmentation method using fully convolutional neural networks that significantly improve the accuracy of fence segmentation. The existing segmentation datasets do not provide accurate labels for fences, thus restricting the data-driven methods for fence segmentation. To overcome this problem, the lab collected and released a novel fence segmentation dataset with highly precise pixel-level ground truths. The lab then proposed a content recovery algorithm based on optical flow, producing a plausible defenced image and video. Center of pressure, COP, is an important measurement of postural and gait control in human biomechanical studies. A vision-based estimation of COP metrics offers a way to obtain these gold standard metrics for the detection of balance and gait problems. In this paper, the lab proposes an end-to-end framework to estimate the COP path length and the COP positions from the 3D skeleton. The lab has provided results showing the predicted COP position versus ground truth from force plate, ML, medial lateral direction, AP, anterior posterior direction, blue dot, COP position for each frame. For more information, please visit ece.ucsd.edu.
I hope you're all able to hear and see the video clearly. As I mentioned, please feel free to either unmute yourself to ask Yi Kuan some questions about his experience in the lab, and or enter your question in the chat. Thank you.
Okay, so my name is Yi Wang. In the following time, I will invite 4 students from our lab to showcase our project. And let me share my screen. So my project is on developing deep learning-based multimodal retinal image processing. Retinal diseases, including macular degeneration, diabetes, and vascular occlusions, are important causes of vision loss and have systemic implications for tens of millions of patients. The role of imaging is critical in retinal diseases. There is important information available on different instruments, but it is extremely time-consuming to precisely colocalize such information manually. For underserved communities in many parts of the world, this time delay may cost patients their sight. So in my research, we focus on developing deep learning-based algorithms for multimodal retinal image processing. In the first project, we developed a multimodal registration technique that aligns multiple imaging technology for colocalized analysis. We develop weakly supervised and content-adaptive neural networks that can achieve high performance with the least amount of label. The proposed framework achieves significant improvements upon existing methods in both the robustness to disease and poor imaging quality. And in the second project, we work on motion correction in 3D optical coherence tomography. OCT is a powerful technique for non-invasive 3D imaging of biological tissues at high resolution. However, eye motion is prevalent in OCT, and the motion artifacts lead to discontinuity in cross-sectional views, which is undesirable for visualization and analysis of disease in 3D. So we propose a convolutional neural network to correct axial motion in 3D OCT. Most conventional methods are not robust to large motion or flattens the bottom layer of the retina. The network we propose can remove large motion based on a single OCT volume input, meanwhile recovering the curvature of the retina. So that's all. Thank you for listening. For more information, you can visit our lab website. So Kun Yao will introduce his work next.
Hello, everyone. My name is Chen Du, and I'm a first-year PhD student in video processing lab. I'm very happy to introduce my research project on the vision-based center of pressure matrix estimation. So can you see the slides?
Yes.
Okay, thank you. So basically, this project focuses on the human balance evaluation based on the computer vision technology. So to be more straightforward, so it is to use a video input to predict the biometrics from the human actions. So what is the center of pressure? So it is the point of application of the ground reaction force vector. So it is basically physical biometric that reflects the balance availability of the young people and older adults. So it is widely used in biomechanical studies, such as the evaluating balance control and injury evaluation and certain disease analysis. So computer vision solutions offer a way to obtain the same summary movement information that the gold standard center of pressure provides, while further offering the information about the 3D movement. So basically, the standard clinical assessment is pretty subjective, and it requires a screening of the clinicians. And the traditional force plate method requires an operator that use a force plate to measure your center of pressure trajectories, but it doesn't provide the 3D information. And computer vision solutions provide both 3D information and can summarize your movement from this 3D information to estimate the center of pressure trajectory. So our work includes the evaluation on both the traditional body on-body marker dataset, such as this dataset, using YCON system, which use the on-body reflective markers to record the 3D movements, as well as the computer vision dataset that we collected in recent years. And our dataset is also one of the largest available dataset for the center of pressure. So this is a very important part in our project. So here we show some demos of the example visualization. So for example, this is a video of a people just standing still, and this is ground truth of its center of pressure trajectory, and this is prediction, so it doesn't move. And here is another example. We can see that the estimation result is pretty accurate compared to the ground truth. And for the movement in different directions, such as medial, lateral, and AP directions, as well as complex movements. So our proposed framework can provide accurate estimation for the center of pressure matrix. And welcome to visit our lab's webpage for more information. It has more details about our research topics. Thank you very much. Okay, next is Queen Yang.
Okay. So can you see my screen?
Yes, we
Yes.
can.
Okay, yeah. So we also have some product about computer graphics areas in our lab. So basically we focus on image-based 3D reconstruction, which includes both learning-based single-wheel reconstruction methods and also some traditional geometry-based reconstruction method. So in the learning-based reconstruction method, we are exploring how machine can reason the 3D world with a single image. So as you can see below here, given a single image as input, we try to use neural network or other techniques to infer the 3D model. Here's some specific topics we are working on. So it's like the better neural network framework, differentiable rationalizations, also the better representation for the 3D data. So in our last year papers, we found that the current learning procedure is problematic as there is some ambiguities in the current data set. So we modified the structures and add a regularization term, achieved better results comparing to the state of the art. Also, we built up a multi-wheel human body reconstruction system. So we use images from multi-wheel and multi-sources to reconstruct the human body. So for the algorithms, we try to simplify the current commercial system for daily applications. We try to reduce the cameras and the GPUs they are using. And we try to tackle the challenge occlusion issues with our normal framework, which basically we try to fuse some learning-based services into the traditional reconstructed services to get a better result. As you can see here, we use the machine learning service to fill out the holes, which is generated because the occlusions. So in the paper we just submitted, we achieved better results. Yeah, that's all for this part. Thanks.
Cleo, can you unshare so Shui can share?
Oh, sorry.
Hello everyone, I'm Shui, and I will introduce the 3D gaze estimation project. So gaze estimation is well established as a research topic in computer vision because of its relevance for several applications, such as gaze-based human-computer interaction, saliency detection, and virtual reality devices. So over the last couple of years, thanks to the deep neural network techniques, gaze estimation methods enjoy significant improvements. So gaze estimation methods mainly include model-based gaze estimation and appearance-based gaze estimation methods. So the model-based one requires high-resolution eye images and near frontal head poses. These requirements are no longer needed in the appearance-based network. Without the extra step, the gaze direction is predicted directly from the eye images, thus it is applied more widely. So in the gaze estimation task, one of the challenge is the head pose variation. The actual gaze direction is defined by head pose direction and eye direction shown in the figure. So this figure illustrates the same gazing target with different head pose results in different eye directions. So in order to solve this, normalization methods are proposed in 2D and 3D settings to remove the head pose variations for more efficient learning. However, our human eyes have a property called ocular counter-rolling. When the head tilts to the side, the eyeball will rotate in the opposite direction. But after normalization, this movement is removed, which is undesired. So this is detail about the reason of this bias. Due to the undesired rotation of the eyeball, the actual gaze direction has a bias delta theta, which influences the gaze prediction precision. So we propose a network to remove this delta theta, and this is the result. So we test on the public dataset and compare with state-of-the-art methods. We can achieve around 70% improvement. Yes, thank you. So this is my overall introduction of the gaze estimation project.
Okay, thank you very much for your presentation. If you have any questions, feel free to unmute yourself or type it in the chat channel.
So we have one question in the chat for our current PhD students. Are most of the topics the lab does medically related?
Not exactly. So there are, I think, 2 projects that is related to the medical department, and for the others, it's not related to medical. So for example, the 3D reconstruction project is not related to the medical.
And just one announcement, we have about 3 minutes left of this session, and then we'll be hosting the major group sessions for you to meet some of the faculty there. But in the meantime, feel free to ask your questions right now via the chat or by unmuting yourself.
Can I ask how big the lab is? Like how many PhD students there are?
So currently, I think there are around 10 or 11 PhD students in the lab. I'm not sure if that counts the most newly joined members. You can find more information on the lab website. It's videoprocessing.ucsd.edu.